by now we have understood that a wire is more than a wire being physical system or a physically made up of with conductors or dielectrics, right? They are to be treated as transmission line whenever their lengths of the wire lengths become appreciably close to the wavelength of interest, so the shortest wavelength of interest. So when that happens, you have to treat wire as a transmission line. So what is this transmission line? If you have obtained an impression that wire being treated as a transmission line is a bad thing, you might be right and you might be wrong. In cases where you don't want the wire to act like a transmission line but the wire is actually acting like a transmission line, then it is a problem, because you don't want the wire to act like a transmission line. You want no delay, you don't want any imperfections caused by the wire itself. However, in those cases, if you have to treat it as a transmission line, then it is a nuisance, it is bad. There are situations, however, for example, you have an antenna, okay, and to this antenna, so you have this antenna up here and you want to transmit something to this antenna, okay, then you need to actually have a cable which would be running from antenna terminals to the function generator or the generator of your signal which you are connecting. In this case, you want to treat this as a transmission line because this is precisely what the job of this wire is. It is actually transmitting energy from generator to antenna, okay. So in this case, you want to know how better I can make this transmission line, what are the different type of transmission lines that are available, and how do I analyze this transmission line, okay, and that is what we are going to occupy ourselves with in this next part of the module, okay. We will be talking about how to model a transmission line and also derive some expressions for voltage and currents on the transmission line, okay. So that is the objective for this particular module, okay. First of all, let us learn to recognize what a transmission line is. Although I have drawn it with only one wire, right, a typical transmission line actually is made up of two conductors, okay. So you have an upper conductor over here, so this is the upper conductor, and then you have a lower conductor up here, right, and these conductors are pieces of metals, okay, which means that they are not always perfect, and these conductors are filled with some insulating material, okay. They could be filled with nothing but air is also a form of an imperfect dielectric or an insulator, so it could be filled with air, okay. You might also have a situation where you have ground plane, okay, so you have some copper, okay, in the form of a PCB, and on top of it you have a small region or a small thickness of some insulating material, and on top of this one you might actually have a metal piece, okay, and then you apply a voltage around to this metal piece and the ground plane, and then if you look at how the waves would propagate on this top metal surface, you will actually be able to model this propagation in terms of this canonical transmission line model, okay. So although we show this type of transmission line, it is not necessarily that transmission line itself looks like these two wires, okay. This is one example of a transmission line, this is another example of a transmission line, this is known as microstrip transmission line, okay. We will see some of these transmission lines later, but all these transmission lines can be modeled by considering them to be made up of two wires, right, and these wires are conductors, and that is actually clear if you look at the microstrip also. The microstrip has one piece of conductor which is the top surface and another piece of wire which is the ground plane, and any voltage that you are connecting is between this top surface conductor and the bottom conductor, right. So you can model microstrip line or a two wire line or a twisted pair of line or a coaxial cable, right. So all these things as this canonical two wire transmission line or two conductor transmission line. And two things you have to recognize. One, the dielectric that is filling the region between the two wires may be imperfect, right. If it is imperfect, then it will carry conduction current plus some displacement current, and we know that in a perfect dielectric there should not be any conducting current. The presence of conducting current implies that there is some leakage conduction current and there will be dissipation because of this conduction current, right, because conduction current is I and I square R losses will be there. There is a second thing, and this behavior of conduction current giving rise to losses can be captured by assuming a set of resistors connected here, okay. Now these resistors are not physically connected, we are only imagining that these are connected, and we assume that these resistors are placed at around delta L by N. So if you have N sections or N resistors, then they are placed at a length of delta L by N. Please note that this is the reality, right? This is a 2-wire model that we have, or a 2-wire physical system that we have, and this right hand side is actually a model that is trying to capture this reality. Okay, so and this way we are capturing the model is that we imagine there are N resistors, okay, connected from top surface to bottom surface, or top conductor to bottom conductor, and these resistors are placed at delta L by N, and this delta L will be taken to be much smaller than lambda. Therefore, each of these resistors can be thought of as lumped circuits. Okay, now that is not just the only thing that happens. Okay, there was current down. Okay, you modeled that current as consisting of resistors or equivalently some conductors, right? And along with that one, there was also capacitance associated with this one, right? So you have a top surface, you have a bottom surface, there will be some capacitance associated. Again, this capacitance will not be at a particular point, but this will be distributed, right? So it would be distributed in the same way as the resistors are distributed. Again, you have to remember that this is a model that we are trying to capture. Okay, so together the resistor and the capacitor will form an admittance, because you have one capacitive reactance as well as one resistive reactance. Together they would form an admittance. Similarly, on the upper surface and just one conductor, when there is some current I flowing, there will be some magnetic field around it, right? So whenever there is a current flowing and then there is a magnetic field, we have seen that there will be an equivalent inductance, right? So there will be an equivalent inductance L, and that inductance needs to be considered. A second thing is that these conductors may not be perfect, right? So if they are not perfect, then there will be some leakage current through this conductor, right, in the form of I square or losses. These things will be incorporated by considering each of these conductors as composed of sections of resistance and inductance. Okay, so this again gets distributed. On the susceptance side, you have a capacitive susceptance and a resistive susceptance. Again, these sections would also be distributed. Each of these sections should have a length delta L which is much smaller than lambda short, so that we can treat each section as a lumped circuit. Okay. However, a collection of such infinite sections will form a overall transmission line, and in order to deal with the fact that these are distributed, we will measure these resistances in terms of ohms per meter, these inductances in terms of Henry per meter, right, and then measure these capacitors in terms of farad per meter, and this conductance in terms of again ohms per meter, or you can measure them in terms of Siemens per meter, because they are connected in parallel. So essentially a 2-wire canonical transmission line can be thought of as composed of an infinite number of stages. Each stage is so small that we can treat them as lumped circuit, and in each stage you will have impedance as well as admittance. Okay, so that is what we mean by that is what the model that we are going to concern, and you can actually see that model over here. Okay, you have each section of length delta z. We are assuming that the transmission line is located along delta z. So each section has a length delta z which is much smaller than the wavelength. Okay, and in each section you have KCL and KVL being true. Okay, and we distinguish this parallel resistor connection by writing this as G and series resistance as writing it as R. As I said, these elements L, R, C and G are called as distributed parameters of this transmission line. This is inductance per meter and resistance per meter, conductance per meter and capacitance per meter. Okay, so this is the model that we are going to consider for a 2-wire transmission line. So with this model, let us try to see what happens to the voltage and the current. Okay, so in big change from a lumped circuit, the voltage here will not be independent of Z. Why? Because you actually have a lot of stages, right? So you have stages and so on. So you can imagine this is stage 1, stage 2, stage 3 and so on. Now when you are looking at transmission line section in a particular stage, you have to give stage number, okay, and inside that stage number you have R, L, C and G, right? So this is what each stage looks like. So if I want to specify the current, I have to specify the current in the form of stage number. Now instead of specifying a stage number, because you are going to consider these stages to be of infinity and distributed point wise, you replace that stage number by a continuous variable. Okay, so at any point z on the transmission line, what is the current? At any point z on the transmission line or across the transmission line, what would be the voltage? This is how the fact that voltages and currents at points on the transmission line are different enters into picture, right. So you are, in addition to specifying how the currents and voltages vary with respect to time, you also have to specify what stage or at what point on the transmission line you are, and that will be captured by writing this as a function of both z and t. This is like thinking of a wave, right. So a wave, we have already seen in the previous modules, has to be specified both as a function of z as well as a function of time, and this is precisely what we are doing here for voltages and currents. We are assuming that voltage and currents, because we need to consider the delay into account, will not behave as simple voltage or current which are just time dependent, but they will behave as though they are waves which are dependent on both z and time. Okay. However, within each unit cell or within each stage, these voltage and currents are essentially such that the lump parameter laws KCL and KVL can be employed. Okay. So consider this nth stage here, which is located at a point z on the transmission line, and then you try to apply KVL to this loop. Okay. Now the current entering this stage is I of zt, and the voltage across the inputs of terminals of the voltage cell is V of zt. Now once you have passed a stage, the current would have changed by a small amount, and that current must be evaluated at the space z plus delta z, that is, it is the next stage current and this is the next stage voltage, right. So now you need to apply KVL around this loop, and when you apply, you will see that this would be V of zt, voltage along this one, minus I into R, right. So that is minus R, because it is not just R, this is R into delta Z. This R into delta Z is in ohms, but R itself is in ohms per meter. Okay. So Ri minus, what is the current through an inductor? L di by dt, right. So it is L delta Z del I by del t minus this voltage V of Z plus delta Z of t equal to 0. You can rearrange these equations by writing this V of Z plus delta Z, V of Z, and then pushing out this R delta Z I plus L delta Z del I by del t onto the right hand side, and then divide both sides by delta Z, okay, and then take the limit of delta Z going to 0. So when you apply limit of delta Z going to 0, you end up with this equation, which states that the first order partial derivative of the voltage is given by Ri drop plus L di by del t or L del I by del t drop here. Okay. Similarly, you can apply KCL to node n, which is this particular node. You can equate what are the currents going and coming out here. The current coming in is I, current going out is I of Z plus delta Z. Then there are two currents which are flowing through this. The voltage here is V of Z plus delta Z divided by C into del V by del Z, and current through this conductor is C into G, right. So current through this one is C into G, and that is what we have written over here. You can again rearrange the equation to obtain an expression for the partial derivative of current, and you will see that this is given by del I by del Z minus of del I by del Z is equal to G V plus C into del V by del T. So you have one equation which describes how the voltage is changing, you have another equation which describes how the current is changing. These two are first order partial derivatives. They are actually very similar to the expressions for electric field and magnetic field, right. So you can actually compare them with the uniform plane wave expressions. We will do that comparison later, but you will, when you do that one, you will see that these two expressions are quite similar to electric field and magnetic field expressions, and you can actually combine these first order equations into second order PDE. How do you do that? You differentiate one equation with respect to t, or sorry, with respect to z, and then substitute the other one, and then we will consider first a case where we are considering no losses. That is, we will assume that the dielectric filling the region between the two wires as being perfect with no G, no conducting current, and similarly the conductors themselves which make up the transmission lines are perfect, therefore R is also equal to 0. So you can combine these first order transmission line equations to get a second order partial derivative equation and partial differential equation, and you will see that that equation is del square V by del Z square is equal to LC into del square V by del T square. Now doesn't it remind you of del square E Ex by del Z square is equal to 1 by V square del square Ex by del T square. I do hope that when you look at this equation you are reminded of that one, and this LC we will denote it by a special symbol called 1 by UP square. Okay, this is the velocity of what? Velocity of the wave. Which wave? Voltage wave, right? Voltage is actually related to the electric field, therefore what we have really written down is the wave equation for electric field. Okay, and this UP is called as the phase velocity and it is given by 1 by square root LC. We already know what the solutions for these type of equations are. They must be propagating solutions. You have two types of solutions, one is forward wave and one is backward wave. Backward waves are generated whenever a transmission line is terminated and some termination is not perfect, so that a voltage wave reaching the termination will get reflected back. Similarly, one can derive an equation for current, and then you will see that the current equations are also in the form of wave equation, which will have solutions in the form of forward current as well as backward current. Please note that this backward current is not the return current. Okay, even the return current will have forward and backward components. This current is the current that we have considered in the top surface. Okay, and that will also be made up of forward and backward currents. Now, if you actually assume that only forward going waves exist and then try to take the ratio of the forward voltage to forward current amplitudes, you will see that that ratio turns out to be a number Z0 given by square root of LC, and this has units of ohms, and this is called as characteristic impedance. Okay, for a lossless line, characteristic impedance is completely real and is given by square root of L by C. So, to summarize, what we have done is that we assumed or we went through, so we will come back to this generalized expression sometime later. So, what we have done is we have assumed a transmission line in the form of an infinite number of stages, each stage consisting of a resistance, inductance, conductance and a capacitance. Conductance modeling the imperfectness of the dielectric, resistance modeling the imperfectness of the conductor, L modeling the fact that there is magnetic field associated with the current, and C indicating that there are region between the two wires actually makes up a capacitor. These values are described in per unit length terms, and therefore these are called as distributed constants or distributed parameters of a transmission line. To obtain the expression for voltage and current waves, we actually ended up using KVL and KCL. We were able to do that one because we had assumed that the section length delta Z is much smaller than lambda short, the shortest wavelength. Okay, and when we wrote down KVL and KCL, we arrived at two equations which are first order partial differential equations, and we solved those equations to show that voltage and currents are actually waves and they will consist of forward and backward waves. Okay, so we will now stop this discussion and then in the next module take up what will be the general excitation of the transmission line and then try to solve for those cases. Thank you.